Until now, we have been assuming that the data is linearly separable, meaning that there is always a straight line to perfectly separate the positive and negative examples. But what if the data is not linearly separable? For example, here you can see that there's actually no straight line that can perfectly separate the positive and negative examples. And the best you can do is that you can have a decision boundary here, and you have some negative examples end up on the left, and you have some positive examples on the right. And this is basically the best you can do. So in this case, if the data is not linearly separable, we'll have to relax the hard constraint that we have before and have a penalty term in the objective function. And specifically, remember that originally we have a hard constraint saying that every data point has to be within a margin that's larger than 1. Basically, the confidence needs to be larger than or equal to 1. And in the case that's not linearly separable, we'll need to relax that. So we will relax 1 to 1 minus c. And correspondingly, instead of only minimizing the square of the length of W, we will need to minimize this square of the length of W plus the number of training mistakes. And the C here is actually a hyperparameter, just to balance these two terms. How large do you want to focus on maximizing the margin, or how good do you want your model to fit your training data? So this C is a hyperparameter that you can tune using a validation data set. Now, one natural question is that how do you penalize mistakes? Because if we penalize mistakes this way, then you're basically saying that all mistakes are treated equally. But actually, it's not, right? Not all mistakes are equally bad. For example, if you look at this positive example, it's actually far away from this decision boundary. So this mistake is actually pretty bad, right? So the natural way of doing this is that we can penalize the mistake according to how much you relax the margin. Right? If the more you relax this hard constraint, then you will be penalized more here. So basically, we'll replace this number of mistakes with the sum of the C. So basically, we can then rewrite the optimization problem in the natural form as we see in this equation here. So the first term is the same as before, and the second is just some linear algebra manipulation. So this is still the margin of our model, and C is the regularization hyperparameter that we can tune using the validation set. And this penalty term is the empirical law. So basically, it says how well we fit the training data. And if you look at this term very carefully, you can see that for each data point, if the margin here is larger than or equal to 1, then we basically don't care. The loss or the penalty here would be 0, right? Because 1 minus something larger than 1 would be some number that probably smaller than 0. Then you're taking the maximum over 0 and this number, meaning that the answer will still be 0. So basically, if the margin is larger than 1, then we don't care. This term will just be 0. But if the margin is smaller than 1, then you're gonna need to have to pay a linear penalty. So in both cases, you need to pay the linear penalty. One is that the margin is larger than 0, but it's smaller than 1. Because in this case, this margin here would be smaller than 1, and 1 minus something that's smaller than 1 would be something that's positive. For this whole term would be positive. Another case is that you actually predicted the wrong class, meaning that the margin is smaller than 0. And of course, in this case, you get a larger penalty, right? And this is actually what we call a hinge loss function. So in a hinge loss function, if the margin or this z is larger than or equal to 1, then the value will be 0. And otherwise, it will be increasing linearly, going upwards. So why do we want to use this hinge loss? The reason is that because ideally what we actually want is a 0-1 loss, right? Because if we classify a example correctly, we want to have 0 loss. And if we classify a example incorrectly, then we want to have a loss that is 1. But unfortunately, this 0-1 loss function is not continuous. Therefore, it's actually very difficult to learn a model using this loss function. And the hinge loss is a very good approximation of this 0-1 loss that happens to be continuous. And this is the reason why we want to use the hinge loss. Of course, equivalently, it's actually trying to maximize the margin and also trying to fit the data as fast as we can.